In this lecture, we're going to be discussing enzymes. In order to talk about enzymes on what they do, what's their purpose, you've got to have a little bit of information beforehand, and I got to follow it up with a little bit of information after you find out what they do. So the first thing I'm going to start with, and you guys have seen these words before, we've talked about them just a little bit, are chemical reactions. Hopefully you remember chemical reactions are processes that chemically combine elements together. I'm going to talk about two major categories of chemical reactions, and I'm also going to talk about two major types of chemical reactions, and that will lead us into what we need to talk about for enzymes. Before I move on to that, all chemical reactions need to obey certain laws in order for them to be successful. All of these laws start with the same beginning. Law of conservation of, and then blank. We're going to talk about the law of conservation of mass in terms of chemical reactions, law of conservation of energy in terms of reactions, and then law of conservation of matter. In a chemical reaction, I have to obey these laws. It's vital that I obey them. For law of conservation of mass, whatever I start with in the beginning, and this would go with energy and matter, I could talk about all of them. Whatever I start with in the beginning, I have to have the equal amount on the other side. So whatever I start with on my reactant side, I've got to have on the product side as well. If I start with 2 grams of hydrogen, I have to have 2 grams of hydrogen on the flip side. For energy, I may give off energy in this one reaction. That energy will then maybe go on and feed the reaction that happens next down the road. So I'm constantly conserving and recycling all of these individual bits. With the conservation of matter, I can't just create something out of thin air. Everything comes from somewhere. So I conserve it and I recycle it. Those are the two big words you need to know for this. Conserve and recycle. I've got to keep it all. It all stays within the universe, and I just keep using it, and I just keep using it. It gets cycled around, it gets conserved, and it gets pushed off to something else. Before we move on, I just want to quickly review all the individual parts of a chemical reaction. So I'm going to give you the reaction to make carbon dioxide. I'm going to take carbon monoxide, CO, react it with oxygen, and I'm going to make CO2. Now hopefully you remember anything that is on the left are my reactants. Anything on the right are the products. No matter what, left reactants, right products. Now the only other part I need to quickly just go over, and I won't ask you to do this on the test, but I'm going to go ahead and introduce it because you'll learn it next year with chemistry, is you've got to balance it out because I have to obey all those laws that I just talked about. Law of conservation of mass, energy, and matter. Right now, my carbons are equal. I have 1 carbon on each side. So right now I'm fine. I'm obeying my law of conservation of mass. However, my oxygens are not equal. I have 1 here, 2 here, so I have a total of 3 on this side. And over here I only have 2. So I am unbalanced. So I've got to balance this stuff out. Concentrate on just your oxygens. Let's balance those out first. Since this oxygen is got an even number, I'm going to leave it alone. Evens are easier to work with than odds. So what I'm going to do is take my odd oxygen and try to make it even. The simplest thing I can add is a 2. So that changes my number of oxygens from 2 and 2, so now I have 4. On this other side, I still only have 2. I've got to make that balance out. I can simply do that by adding a 2 in front of there. Now I have 4 oxygens. Go back and look at your carbons. I have 2 carbons over here, 2 carbons over here, so now I'm all balanced out. With 2CO plus O2 yields 2CO2. Expect you to know reactants, products, and then these numbers that you put in front, coefficients. Those are the 3 parts that I expect you to understand and to know. Now for the categories. There's 2 major categories for a chemical reaction. One category makes energy. One category needs energy. Let's talk about the one that makes it first. Exothermic reactions. Because it says exo and thermic, which means giving off heat, you now know the definition of this. These reactions release energy. This energy can be in the form of heat, light, or sound. These reactions also occur spontaneously. Love that word. They do not need any help, is basically what that means. They occur on their own. They don't need any input. They will just go. The flip side of that coin are reactions that need energy, and those are endothermic reactions. Endo and thermic needs energy. So these absorb energy. They need it. They require it. They will not occur without an energy source. And a lot of times this energy source is going to be heat. I will be coming back to this one because this one is where enzymes come into play. So this one is specific to enzymes, and we'll talk about why in just a minute. Now in exothermic and endothermic reactions, I can talk about two major types of reactions. There's several different types of reactions. I'm only going to ask you to know two. The first one I want you to know are synthesis reactions. These are simply what they are. Synthesis. Synthesis means you make something. So for these, I start with two reactants and I make one product. You make something, such as when I make water. H2 plus O2 yields H2O. I went from two reactants over here to one product. Flip side of this one are decomposition reactions. Decomp, decompose, break down. This is when you have one reactant and you go into, say, two products. You break down the reactant into its original elements. And I can show this with the exact same reaction. Say I took water and I broke it back down into what I had originally. I went from one reactant to two products. For the two categories and the two reactants that we just talked about, you can kind of guess that there are buddies in that system. The one category typically goes with one type of reaction and the other category maybe goes with the other type of reaction. A lot of times an exothermic reaction, I'm going to just put exotherm, buddies up with a synthesis reaction. Not always, but a lot of times synthesis reactions are spontaneous. They will occur without any help. Whereas an endothermic reaction usually buddies up with a decomp reaction. Reason being why these two are buddies is because of a very special term, and we call it activation energy. Activation energy, the reason it goes with those two things is because activation energy is the amount of energy needed to start a reaction. If I want a reaction to begin for an endothermic, for decomp, a lot of times they need help. The reaction itself requires a massive amount of energy input. And the way to get around this is to lower this activation energy. If I can lower the amount of energy it takes for me to start a reaction, I can get the reaction going a whole lot sooner. The things that cause all of this to happen lowers the activation energy, and I'm going to start calling it AE. These are where enzymes come into play. Their sole job is to lower that activation energy. Enzymes are very specific proteins that act as a catalyst to speed up a chemical reaction. So the essence of this is that enzymes decrease the activation energy needed for a reaction to start. That's their main job. Enzymes are very, I can't stress that word enough, very specific. Usually there is one enzyme per reaction. And when we get into Unit 3, when we start talking about biochemical pathways, you will see this come into play, that certain parts of photosynthesis, certain parts of cellular respiration, they all have a unique enzyme that will catalyze that part of the reaction. Very, very, very specific proteins. The way you name these, they're usually named for the specific reaction they catalyze. So for example, when we get into DNA replication, DNA polymerase is the enzyme that helps synthesize the new strand of DNA. Whereas you have helicase, which unzips the DNA so that DNA polymerase can get in there and do its job. So every single enzyme has a very specific job. Enzymes are regulated by anything that affects chemical reactivity. So I could talk about pH, I can talk about temp, or I can talk about feedback loops. And I hope you remember what those things do. If you don't, think of an air conditioning system and hopefully that jogs your memory. So in some ways, enzymes can be controlled depending on what's the acidity that they're placed in. If it's too acidic, then they're not going to work because the enzyme itself can become denatured and it won't catalyze the reaction it's supposed to get. If I lower the temperature too much, then I basically would freeze my enzyme in its place and it's not going to work. Feedback loops, I get signals from my nervous system, my endocrine system, that says, okay, whoa, we're good. You can stop doing that. And it will shut down the enzyme for just a little bit. And then when it gets to the point where I need it again, it'll come back through and turn itself on with the help of other proteins and enzymes along the way. The way an enzyme works when it's catalyzing a reaction, you have several different parts that are all working together. How it is described is called the lock and key mechanism. With just the name right there, what in the world do you think this means? Hopefully it's bringing into mind your door key and the lock on your house, or the car key and the lock on the door. I told you that enzymes are very, very, very specific. So only one key can fit into the lock. There is only one lock for a specific key. There's a little bit of terminology you need, and then we will talk about the lock and key mechanism more in class. One thing I need you to know is substrates. These are the reactants that are going to be either put together or decomposed. So I could either do a synthesis reaction this way, or I could also do a decomp reaction. But your substrates are called your reactants. The enzyme, which you should already know what that is, but on the enzyme, you're going to have active sites. These are where substrates bind to the enzyme. When I get substrates interacting with my enzyme, it becomes the enzyme substrate complex. When enzyme and substrate interact. Just know the terminology for now, and then when I get you in class, we will go through this in much more detail. But this will be the main thing that we talk about in class. To finish out this lecture, so I've filled in the front story of enzymes with reactions and endothermic, exothermic, decomp, and synthesis. Told you what enzymes do. Now let's talk about one way they are controlled or regulated. And one of the things that I said was pH. pH means I'm talking about acids and bases. This will play into the lab that you're going to do, so I'm going to go ahead and introduce it here. Plus, you guys should be fairly familiar with this information. To determine if something is an acid or base, how do I measure it? The pH scale. Something is considered acidic or basic depending on where it lands on the pH scale. If the pH is equal to 7, I'm said to be neutral. So if I had a pH scale right in front of me, it goes from 1 to 14. Right in the middle is 7. So that means I am neutral at this point. If I go anywhere above 7 and go up to 14, I am considered basic. If I go anywhere from 7 down, I am considered acidic. Acids, pH is always less than 7. A weak acid is considered anywhere from 4 to 6 on the pH scale. And I'm talking about tomato juice, even your urine, if you really want to get technical with that one, would fall in a weak acid. Then a strong acid would be anything from 0 to 3, or 1 to 3, 0 to 3. This could be hydrochloric acid, soda. Think of Coke. I could throw a penny into Coke and it will eat some of the penny away. That's why I don't drink soda. And then also another one could be vinegar. That's why a lot of people use it as a household cleaning product. Usually these taste sour. They are corrosive to metals and can, I'm running out of room, can burn your skin. If you were using a weak acid and you got some on you, you definitely notice it with a strong acid much more quickly. But even with some weak acids, if you get it on your skin, you will feel kind of a burning sensation on your skin because it's starting to break down the cells that make up that part of your skin where you got it. And so you can actually feel it kind of burning your skin. Bases. The flip side. These have a pH greater than 7. Weak bases are from 8 to 10. And examples of this would be baking soda, seawater, things like that. A strong base is anything from 11 all the way up to 14. And the examples of this would be soapy water, actually. Soapy water is actually kind of strong, so it can eat through the gunk that's on your skin. And also bleach, ammonia. And that's also why that one is used as a pretty good cleaning supply. Bases taste bitter. They also feel slippery. If you get them on your skin, think of soap. Soap is very slippery. And these can also burn your skin. So basically, moral of the story, when you're messing with acids and bases, don't get them on you. It's bad news bears. This is where I'm going to conclude your lecture. When you get into class, we will talk about the lock and key mechanism, and we will watch a video on that. Plus, I will talk to you about why it's so important to know about acids and bases in terms of cells. Why is that important? What is pH mean to us as a human being? So we will talk about those two things in more detail when you get to class. So I will see you soon.